Hi, welcome to the Chico Math Lab Fun Probability Problem Solving Sessions. So in today's video, we're going to talk about the variable transformation technique. Especially, if I have two variables and how do I use the technique and try to find the joint PDF of these two new variables here. Okay, so now let's take a look at this example I'm going to use and to demonstrate how do we do the variable transformation technique. So here we said let xy be two random variable with the joint PDF of f of xy equal to the 4xy, with x is from 0 to 1, y is from 0 to 1. Now I define the two new variables, z is equal to x plus y and w equal to the x divided by y here. All right, so now I want to find the joint PDF, the z and w. When we try to do the variable transformation technique, I feel that the hardest part is try to, after you find the joint PDF, you want to find the domains of the new variables. And we need to be extremely careful here. The other part is kind of like very mechanical. Okay, so the kind of follow the step and you would get it. Okay, so now let's take a look at this example and let's go to the whiteboard and let's work on these problems here. Okay, so in here, like I mentioned here, let's try to write here. So the f of xy, this is a very simple joint PDF, right? So it's 4xy, and with x is from 0 to 1, and the y is from 0 to 1. Okay, so now I have the z is equal to the x plus y, and w is equal to the x over y. So the goals here is we need to use some algebra and try to solving for. So the goal is try to solve what is x equal to and what is y equal to. Okay. All right. Now, because w equal to the x over y, right? So from this one, I know that x is equal to what? W times y here. Then also, so the z is equal to x plus y. And since from the second equation, I know the x is equal to wy, so this one I can write as wy plus y, correct? And then I will take the y out, and then this is w plus 1. Okay, so then I can solve it for y here, right? So the y is what? If you take a look at this one and this one here, right? So the y will be equal to the w plus 1 and the z's here. So now I achieve my goals here. This is x equal to the wy and the y equal to the z over w1. So the next task I'm going to, I'm sorry here. Here, be careful here. I did not achieve my goal yet. Okay, so here, this is x equal to the w times y here. Now from the y, I plug back in. So x equal to what? wz, w plus 1. Okay, now I can claim I achieved the goal. So I can transfer both x and y to function of the z and the w. So the next things here is just like we learned in the calculus. What we need to do? We need to find the Jacobians, right? So the Jacobians here is like a rho x is the absolute value of the rho x, rho z, and rho x, rho w, and then this is rho y, rho z, and rho y, rho w, right? So we want to find the absolute value of this. Okay, so now in here we can just say here, just do the calculus, the x take the partial derivative with z. So what you have, this is w plus 1. Then x take the partial derivative with w, then you need to use the quotient rules, right? So this is w1 to the square, and then the top here, I believe, after you use the quotient rule, this will be z. So, okay, you can double check that. And then the rho y, rho z will be 1 over w plus 1. And rho y, rho w is a quotient rule again. So it's w plus 1 to the square negative z's here. Then we find the determinant, so it's just like you times this 2 minus you times this 2, right? Okay, so I'm going to have w plus 1 to the third power negative zw, and minus w plus 1 to the cube the z's here. So this is the w plus 1 to the third. You take the negative sign out, and you will have w plus 1. Then finally you simplify to the negative z, w plus 1 to the what? To the square, right? So then I know the absolute value of the Jacobian will just be absolute value of negative z, w plus 1 to the square. So this is z over w plus 1. Okay, now after this, I can substitute right to the this function is here, my original f of x function. So now I know my gzw, this is the zw. So you just plug the x into the, the x equal to wz. So it will be 4 times wz, w plus 1 times y times z, the w plus 1 times what? Oh, here, so be careful, this is square, times the Jacobians, right? So the Jacobian is the z, w plus 1 to the what? To the square. So if you simplify it, so this is w plus 1 to the fourth power. So this is 1, 2, 3, so z to cube. So this is 4wz to the cube. So like I said, this is the PDF here, right? So this is a PDF, joined PDF of the z and the w. Like I mentioned, the hardest one is to try to find the domain of the, the zw, because right now we know here for the XY joined PDF, X is from 0 to 1, Y is from 0 to 1. Okay, so in order to do that, here is, okay, so I typically do like this way here, all right? Okay, so this is my X, this is my Y, right? And so this is the 1, and this is 1. And so here, and here, right? Okay, so this is the 1, this is the 1. So this square is what, what is the domain. So now I want to do here is like, I want to put this line segment. I will say this is my R1, so that's the original. So I'm going to color coding that. It will be easy later. I color code my, after transformation, what is my domain? So this is R2. And then I will do here, this is my R3 here, right? And then this is my R4. Okay, so now I'm going to transfer that to the new domains here. Okay, so let's see the R1. R1, for the R1, what's that mean? That means y equal to 0, right? So y equal to 0, that means y, that means z, the w plus 1, equal to what? Equal to 0, right? So that means z has to be equal to 0. All right, so now I'm going to graph my new domains here. Okay, maybe, all right, so here, okay. All right, so maybe I want to put, let me put this line a little bit higher. Okay, all right. So the first ones here, we find z equal to R1, z equal to 0. So if I put this is my z-axis, this is my w-axis. So I will say the z equal to 0, right? So that means the R1 transfer to this new domain. I will call this is S1. Okay, so now let's take a look at the R2. And that's why I'm color coding that. So what is the R2 mean? R2 means x equal to 1, correct? Okay, so if x equal to 1, so here's my x. So I know the WZ and the W plus 1 equal to 1 here. Then I know the WZ equal to the W plus 1. Okay, so then I will have, I move the W over, so W times Z minus 1 equal to 1. So what is this one give me? This will give me the W is equal to 1 over Z minus 1. So this is a rational function, right, between the W and Z with Z shift to right with 1. Okay, so let's see what is this one here. So this is ones, right? And because it's shift to the right-hand side 1, so it's a rational function. So that means, okay, so this will be, so here, the R2 here will transfer to this, right? So transfer to this lines here. Okay, now let's take a look at R3s here. R3, what is R3? R3 is y equal to 1. Okay, so y equal to 1. Okay, so I put y equal to 1. So it's z, the w plus 1 equal to 1. So I will have z is equal to the w plus 1. Or you can say w is equal to the z minus 1. So what is w equal to the z minus 1? It is what? It is lines, right? So I can say this is 1. All right. So when z equal to 1 is equal to 0. So so the R3, I can transfer to here. Okay, so this will be my I should say S3 because that's my new things here. So this is S3, my new boundary, and this one is my S2, the new boundaries here. Okay, so my last boundaries here is R4. Okay, so R4 is what? R4 is x equal to 0, right? So x equal to 0, that means WZ and the W plus 1, this is equal to 0. Then I know I'm going to have what? W equal to 0 here. So you might ask why you said WZ equal to 0, not the z equal to 0, right? So, okay, so if you see the z equal to 0, then the y here will be 0 also. So this is only x equal to 0, not like the not the both x and 0 and y equal to 0 is not at the origin. So that's why it's w equal to 0. So what is w equal to 0? So w equal to 0, that means this that is z-axis here, right? So this is my S4 here, okay? So this is my S4, and since now I'm going to, right, so I know where is my the boundaries here, because I'm going to bound by those 4 lines, right? S1, S2, S3, S4. So I know this is my new boundaries here. Okay, so this is my new domain for the W and Z is bounded by, you transfer the old domains here. Like I said, when you do the transformation, the hardest part probably it will be try to find the new domain for after you did the transformation. Okay, so now after we know this is the boundary, and then this is my joint PDF, right? So don't forget, so you need to write at the end of this PDF, and then you write on your boundary. So I know here, the boundaries here will be the S3, so this part, right? So it will be, so the first thing here will be W is between, right? So the W will be between Z minus 1 and what? And 1 over Z minus 1. Okay, so this area, let me try to, okay, so this area, this area is really, is from the S3s, right? So it's here, all right, so that's what I'm trying to cover this area. And also you still have the other one need to be covered. So that's why then after that, then you need to say the Z is from where to where. Z is from 1 to 2. You can find this, this point is Z equal to 2 here. And also what? Also W, the W is the W axis here is from 0 to infinity, right? And Z from so this is from the 0 to infinity. This one's here, and what? And from what the Z is from 0 to what? 0 to 1. So you will have these 2 regions here, right? So you will have these 2 regions. This is one region, and this is another regions here. Okay, so this is the another region. So that will be your new domains here, right? So that's why I say it's kind of like the other part is very mechanic. Just use the like calculus 3, the variable transformation. So we just need to be very careful about the new domains here. All right, so that's it for today. I hope you find this helpful, and you find this kind of fun to work on this problem. All right. Talk to you on our next time, see what we can do here. All right. Okay. And so I guess talk to you later now. Have a good day. Okay. Bye.